Watch him turn up now. Okay, so we've introduced the idea of quantum as the notion that energy comes in very small packets, that it's a discrete quantity rather than a continuous quantity. Now, that doesn't mean that you can't have of energy that you want. You can. It's just you need to go find a process that produces a quantum that is the same size as that piece of energy that you require. For large amounts of energy on a human scale, it doesn't really matter. Are so utterly vanishingly small that you just get yourselves a load of quanta. But if you are a atom and you're talking about electron transitions in orbitals or something like that, then you need to find yourself a photon that's appropriately sized, and not always is that available. And we saw that with the photoelectric effect, that sometimes processes can't occur because of the quantization of light. Now, although this is a radical idea in its own right, it's not that crazy. We've never really observed light in great detail because it's very hard to observe. And really what we've done is restrict ourselves to measurements of processes that occur it and measuring the speed of it. And we've managed to do some wave-like phenomena with it, like diffract it, refract it, reflect it, disperse it. Look those words up if you don't remember what they are from the waves topic. And so we just drew this conclusion that because light could do loads of wavy things, then clearly it must be a wave. But actually, when we reflect, we don't really know that much about light, or we didn't at the time. So to reframe it so that it's actually a stream of particles isn't actually that crazy an idea. It was radical, and it did take genius to grasp the idea and see it for the potential that it had. But to be honest, it's not that great a leap to say that energy comes in little packets. After all, matter's been coming in little packets for a long time. We conjectured the idea of atoms, that all matter can be broken down into discrete lumps 2,000 years ago. And although it was only kind of late 18th century when that idea came into its own, and actually late 19th century, early 20th century before we actually had any proof of it, it's been a long established idea that matter comes in little lumps and that matter is a particle. So really, it wasn't that big a leap to go to maybe light is a particle as well. We just needed to come up with an explanation for how particles can behave like waves. And that was the birth of quantum mechanics. How can it be that something that is a particle tricked us into believing that it was a wave? What is light capable of that could do that? Because certainly, if I give you a bag of marbles, you're not going to suddenly believe you've got a bag of liquid on your hand with waves sloshing around on top of it. How is the photon managing to convince us that it's a wave when it isn't? So lots of ideas were put forward along the lines of, you know, water molecules are discrete, but they do manage to create an ocean with waves in it, on it. And maybe it's just that. Maybe it's just when you've got a very, 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 very large number of photons that you find this wave behavior. Maybe it's a kind of group behavior rather than an individual behavior. Unfortunately, that turned out not to be the case. And that began to reveal the notion of the very, very weird behavior of quantum mechanics. So, for instance, an experiment that is possible, that has happened, is that you can produce a light source that has an incredibly low intensity, so lower intensity that you can really consider that the photons are being released almost 1 a second. And so when the photon travels, it really does travel all on its own without any photon mates. And if you shine the photon at a diffraction grating, you remember shining laser pens at diffraction grating, and you saw that the light split up into all those little dots, or even with a double slit, it made kind of bands of light, dark, light, dark, light, dark, and that was just 2 slits. You remember doing that, and you remember us explaining it to you that this was a wave behavior. Well, it turns out that when you shine photons at double slits or a diffraction grating, 1 photon at a time, and you just mark on a screen where the 1 photon landed, and then you just leave the experiment running so that there's only ever 1 photon in the experiment passing through the double slits, 1 photon at a time. Clearly, 1 particle has to go through 1 slit or the other slit, or in the diffraction grating, it has to pass through 1 of the gaps. It doesn't pass through all of the gaps, surely. It just passes through 1 gap. So how can it possibly, as a particle, how can it possibly produce wave-like behavior? And yet the stunning thing that was discovered was that it does. When you shine the photons through 1 photon at a time and they come out the other side, you just put a little dot everywhere a photon lands on your screen, and over a period of hours, it builds itself up into a pattern of bands of light and dark and light and dark and light and dark. And the discovery was that, yes, light is a particle, but it's a particle that moves like a wave. It moves like an extended object. In some manner, the photon manages to pass through both slits or all of the slits of a diffraction grating at the same time, somehow interfering with itself to exist as a photon when it interacts with electrons in atoms, but exists as a wave as it travels. At the start of quantum physics there, we have to abandon the distinction between the particle and the wave at an atomic scale. Photons are able to be shown to be absolutely particles in some situations and absolutely waves in other situations, which means that the photon of light is neither a particle nor a wave. It's a photon. It behaves in a photon-like way, which we try to impose human-sized analogies onto. We try to describe it like, well, maybe it's a bit like a marble, or maybe it's a bit like a water wave. But in fact, it's important to notice that these are just analogies. And actually, a photon is neither a particle nor a wave. It's a photon. When it interacts with electrons in atoms, it's absolutely a particle. But when it's traveling between its interactions, it's absolutely a wave. It's a photon, not a particle or a wave. This is referred to as wave-particle duality. And that's what today's lesson's about. I don't want to say too much more about the photon, because what I'm going to say needs to be in the context of not photons. So this brings us on to the next stage in our journey. And a guy called Louis de Broglie, which is spelt de Broglie, so make sure you pronounce it correctly, Louis de Broglie. He had this radical idea one day. I'm sure others did as well, but he was the one that ran with it and whose names got attached to it. Louis de Broglie said, well, you know what? If we got the photon so very wrong, if we thought all these years that wave-like phenomena on a microscopic scale were waves, but in fact it turns out that they're particles, but in fact it turns out they're really wavicles, what else have we got wrong? Might it be the case that all subatomic entities are these wave particle duality composite objects? What if electrons are like the photon? What if what we've been thinking of as an absolute concrete particle all these years, what if it's not? What if the electron can do what the photon can do? And why stop at the electron? What about atoms? We think they're pretty spherical, pretty discrete. I mean, that's the whole point of an atom, isn't it? That it's a solid lump of matter, a particle in its purest form. What if we got that wrong? What if atoms are really wave-like at a microscopic scale? And why stop at atoms? What about molecules? In fact, what about people and tables and planets? Might we have got the whole notion of discreteness just wrong? And it caused a massive revolution in physics. So much so that probably a third of all of physics today is what we would call quantum physics, which is at its core based on this notion that at the very smallest scales, the distinction between discrete lump and smeared out wave is not really much of a distinction at all. So we need to talk about our friend, the electron. So Louis de Broglie realized that an idea is just an idea unless it's testable. And so he needed to provide a framework, a model that would produce predictions that could be verified by experiments. And the way this works is that you guess a whole load of possibilities, and then you test each one in turn, and you throw out all the ones that are wrong. And eventually, through a little bit of educated guesswork and a little bit of luck, eventually you stumble across something that works. And eventually Louis de Broglie stumbled across this. Oh, no, that's not very helpful. Okay, so this is Louis de Broglie's eventual suggestion. He's suggesting that what we consider to be particle-like objects like electrons, atoms, cars, planets, they have a wavelength from their wave-like nature that is inversely proportional to their momentum. Now, he tried lots of ideas before stumbling across that. And so you're not supposed to look at it and see wisdom and think, oh my God, that is so utterly obvious. You're not supposed to be thinking that. But that was his prediction that was finally verified in an experiment. So I'll show you the experiment and you can get an idea for it. So in this formula, we need a constant of proportionality. And it turns out that when he did the experiments, or had someone do the experiments for him, the constant of proportionality turned out to be our friend Planck's constant, one of our fundamental constants of nature. And so we shouldn't particularly be surprised by that, perhaps. So wavelength is equal to Planck's constant divided by momentum. But that really comes into its own when we remind ourselves what Planck's constant is. So we're looking at wavelengths here that have a default starting value of 6 times 10 to the minus 34 of a meter. 10 to the minus 34. If the momentum was 1. Good morning, Max. Nice of you to join us. So 10 to the minus 34. I mean, just think about that for a second. An atom has a diameter of 10 to the minus 10. A nucleus has a diameter of about 10 to the minus 15. And individual protons are around about 10 to the minus 15. 10 to the minus 34 is 10 to the 19 times smaller than that. It's not like halfway there. It's a 1 followed by 19 zeros. That's what, 10 billion times smaller than a proton. So if you go pick yourself up, I don't know, a liter of milk out the fridge, that's going to have a mass of about 1 kilogram. And you carry it across the room at 1 meter per second. Then that carton of milk out your fridge has now got a momentum of 1 kilogram meter per second. And so De Broglie is suggesting to you that that object that you're holding in your hand is not a particle-like thing. It doesn't have well-defined edges. It's wavy, it's smeared out, it's spreading its little tentacles out into the universe and trying to escape from your hand as if it wasn't in a carton, as if it was just liquid in your hand about to slop through your fingers. But then we find that the wavelength of the carton of milk is 10 billion times smaller than a proton, which means that its wavy-like nature as it spreads out into the universe is 10 billion times shorter than a proton. So you don't notice its wave-like behavior. You don't notice it waving. You don't notice it smearing out. It's not fuzzy in the space in front of you. You do not look at it and go, that's weird, my milk's gone all fuzzy. It doesn't work like that because the wavelength is so utterly small. And so you, the milk, the table, the planet, we all just have so much momentum compared to a nucleus that the wave-like nature is so utterly negligible that it really is okay to totally ignore it and pretend it's not even there. But not so the electron. So let's have a little look at the electron. Now, in this formula, that wavelength is going to start becoming a lot smaller than 10 to the minus 34 if we start dividing it by a number that is a lot smaller than 1. So if you've got a little piece of paper in front of you, you can do a quick calculation. So let's pretend that we're looking at electrons. So the mass of an electron. Anybody remember roughly ballpark area what the mass of an electron is? Shout out, 10 to the minus
31.
Correct, 10 to the minus 31. And let's have our momentum traveling at, I don't know, 10% the speed of light. Anybody remember what the speed of light is?
300 million meters per second.
So if we take 10% of that, then that's 30 meters per second. So let's have a go at this calculation on your calculator. We'll do the mass of an electron that's traveling at 10% the speed of light. So the mass of an electron is around about 9 times 10 to the 31, minus 31. And let's have it traveling at 10% the speed of light, 3 times 10 to the 7. Let's just have a little go at that on your calculator. Okay, when you got an answer, just shout, or actually stick it on the chat. Just tell me what kind of power of 10 you get in. Just give me the index from the power of 10. Okay. So, although that's very small, it is kind of atomic sized. And that's important, because if it's roughly the size of an atom, it's also roughly the size of the separation of atoms in a solid object. And you might remember from when we did diffraction through a double slit or through a diffraction grating, that there's a rule about diffraction. Diffraction happens most strongly when what criteria is satisfied? What is the rule of thumb for getting maximum diffraction when it passes through double slits or passes through a diffraction grating? Do you remember? Just shout it out.
When it's the same size as the gap it's going through.
Correct. When what is the same size?
The wave.
Never use it. The wave
Length.
Correct. Yeah. So we're predicting that a bog standard normal electron, it's quite normal for an electron to be traveling at about 10% the speed of light. A bog standard normal electron should exhibit wave-like behavior with diffraction and interference and superposition if we can shine it through a gap that's around about the spacing of atoms in a solid object. So that's a doable experiment, right? We are predicting that these solid little objects, these electrons that are absolutely 100% particles, no question at all, apparently, if we shine them at the right object that has just the right spacing of its atoms, we should see wave-like behavior. We should see the same kind of thing as when we shine a laser beam through a diffraction grating. So let's try it. So if we were at school, I could show you an actual experiment, but we're not. So here's a video of one. Turns out that the correct amount of spacing is actually really easy to get hold of. It turns out that carbon in carbon graphite roughly has the right amount of diffraction, right amount of spacing. Right, let me know if the video doesn't stream properly, because I'm downloading it at the same time I'm uploading it. It might be easier for me to just post the link. In fact, well, I'll try it. Nothing much is happening in this video. Okay, if I just pull this back a little bit. Do you remember this object? Have you used this really big light bulb-like object in class with Mr. Mellings?
No, I don't really have.
No. Okay. Better remind us when we're back in school to show you this. I mean, it comes up a lot in lots of different topics, so you'll definitely meet it at some point. This is an electron gun. So what we've got down here, this is where we plug the wires in and where the connections are. And then that bit there is, can you see the mouse when I'm moving the mouse around?
Yeah.
Yeah. Okay, so this bit here is just a bulb, like you would find in a car headlight or something like that. It's just a bulb. And when it's turned on, this bit just gets really, really hot. And the electrons that are in the wire have got so much kinetic energy that if we just give them the slightest little excuse to leave, then they would much rather follow the light off the bulb than actually stay in the wire and carry on. So water molecules right on the edge of evaporation, we just need to blow on it to encourage the electrons to leave in the analogy. So what we do instead of blowing is this object here, we charge up to be very, very, very positive. And what happens is that and when I say very positive, I mean like 5,000 volts kind of very positive, and it attracts the electrons out of the filament of the bulb, and instead of staying in the circuit and flowing back to the power pack, they come flying out of the filament along with the light, and they go flying through this gap, and we put a little hole at the end of the gap, and they come flying out of the gap. And so across this, it's a big glass ball because we've made it evacuated. We've sucked most of the gas out from inside, so it's largely a vacuum inside. And so we've got a beam of electrons flying across this gap. And then at the end of the gap, oh, we're going the wrong way on the video. Back. No. There's the bulb. You can see it. There's the connection for the 5,000 volt supply. Yeah, we got that. No, I want to see the end. End. There we go. Pause. On the end of the video here, we've got on the end of the path of the electrons, that's some phosphorescent paint. So when electrons strike it, it causes little flashes of light. So that's the basic idea. We're going to fire some electrons at the at this phosphorescent paint. So when you first turn it on, you just get that dot. There it is. And that's just a very, 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 very thin beam of electrons that are just sailing through the apparatus and hitting the phosphorescent screen at the end. Now what we do is place in the way of the beam a very, very, very thin sheet of carbon graphite. And all of this produces is an array of atoms in the path of the beam. So it's 1 or 2 atoms thick, but it looks like we've punched a load of holes in a big steel plate or something like that. So the atoms are fairly solid, but where the atoms nestle together, because they're basically spherical, there's that little gap in the middle of the 4 atoms where that's basically a hole, a gap. Now it's a little bit different to the diffraction gratings that we were using, because in the diffraction gratings we had lots and lots and lots of parallel lines that made up the gaps. Now what we've got is lots of little dot-like holes in a grid-like format. So there's going to be a 2-dimensionality to it. So whereas when we shone laser beams through through the lines, we just got a row of dots. Now the whole thing is a bit more 2-dimensional. So we're going to get a 2-dimensional image rather than a 1-dimensional line. But this basically is what happens. You have to turn the voltage up from the gun bit by bit by bit to get the electrons traveling with just the right momentum to match the wavelength, to match the separation. But look at that right there. That is absolutely a diffraction pattern. Can you see it all right? Is it coming through on the video?
Yeah, it's coming through fine.
So here's our central maximum, just like we've got when the laser shines through the double slits. And then we've got a darker area, and then we've got another maximum. Then we've got a darker area, and then another maximum. Then a dark area, then another maximum. And we can, again, you just told me that as long as the wave, it'll happen maximally when the wavelength is perfectly tuned to the separation of the atoms, to the gap spacing. So if we play with the voltage dial on our gun, that gives more or less kinetic energy to the electrons, which gives them more or less momentum. And by de Broglie's formula, the wavelength is inversely proportional to that momentum. So somebody is playing with the voltage dial on the power pack, and as they tune it to be just right, then we get more or less spacing, more or less spreading out of these rings. So you go, they're just moving it up and down, just trying to get the maximum out there. Okay, so what this is showing is electrons aren't particles. They behave a lot like particles because we've been assuming they've been particles for a very long time and never noticed that they aren't. So most of the time in most situations, it's their particle-like nature that we observe and we see. But they have another side to themselves. They have a wave-like nature as well. And if you just put an electron in the right circumstances, it behaves like a wave. So sometimes it exhibits its particle-like nature, and sometimes it exhibits its wave-like nature. But the take-home from this is that it is neither particle nor wave. It's an electron. It's a subatomic particle. And as we found with the photon, we have to alter our analogy in our head. Electrons are not tiny little marbles. They're not tiny little grains of sand. The subatomic world does not behave like the macroscopic one. And this is taking away from us a massive crutch that physicists use. We work using analogies. We take a phenomena that we understand, and we say about a phenomena we don't understand, what if it's a bit like that one? And then we model it as if it's a bit like that one. And this allows us to develop models of the unobservables by pretending that they're like an observable. Well, turns out that's not going to work anymore. And from about, well, the last century or so, which sounds like a very long time, but considering these ideas go back 2,000 years, the last 100 years is relatively recent. For the last 100 years or so, we've had to be getting our head around the idea that when we are considering sub-processes, analogies aren't our best bet. About 100 years ago, we started relying more on equations than we ever have. And a whole set of equations were developed that are now referred to as the quantum wave equations. And it takes the idea that all particles are inherently wave-like, and they obey this equation. So by all means, after the lesson, if you're interested, just do some Googling of the quantum wave equation. It went through lots and lots and lots of different formats, just like Newton's laws evolved over time and eventually became relativity. The quantum equations evolved over time. It was like pressing the reset button and going back to 1666 when Newton was sitting there working out the equations of normal-sized mechanics. Now people have had to go back to the drawing board and start all over again with equations for subatomic mechanics, quantum mechanics. And it was like starting all over again. You got to get yourself into the mindset of being a physicist in 1905 when you thought everything was okay and everything was finished and physics was done. All we had to do was sort out the consequences. And now we're starting all over again with an utterly blank piece of paper. It was to the new generation that had the energy and then the enthusiasm for this. Names like Bohr, Heisenberg, Schrodinger, names you might have heard of, all started to develop the new mechanics. They were the Newton of their day. And they developed equations that worked, starting with things like Einstein's Planck's, Einstein's E equals HF, and now de Broglie's lambda equals 1 over p, or h over p, as their starting point. But that just maps from one set of variables into another set, from the particle variables to the wave variables. What they needed was a Newton's second law. They needed a dynamics. How will the objects move in time? They needed to put a time aspect into it. So Newton's second law had the concept of force is basically equal to the rate of change of momentum. They needed their own starting point for that, and they found one, and they developed it. And if we'd have been able, I don't think we're going to be able to go to CERN in October. Right? It's not going to be possible. Everything's locked down like it is here. But should we ever get to a CERN gift shop, you can buy T-shirts and hats and pens and badges and things with the wave equation written on it. It's like buying a T-shirt that says F equals ma on the front of it, but quantum. It's very complicated. You should look it up. It's called the Lagrangian, which always strikes me as like something out of the Matrix or something. So yeah, Google the Lagrangian of quantum mechanics and you'll see it in all its glory. And it looks very complicated, and you won't recognize the notation because physicists have invented their own mathematical notation to express the equations. But this equation has consequences. It predicts how subatomic objects will behave. But the difference between that and Newton's second law is that Newton's second law deals with forces and masses that can be observed and measured, and you can see what they mean and what they do. And when you use a snooker cue to hit a snooker ball, you watch the ball move across the table and you can see the law being enacted right in front of your face. And so you can constantly check every single stage of it that it's correct. The laws of quantum mechanics don't work like that. What they do is you give a set of starting points, which is where the particles are now and how they're moving now. And then you move the time dial forward in the equation a bit, and it'll tell you what they're doing later. What the equation doesn't do, which is of real fundamental difference, is it doesn't tell you how or in what manner the in-between bit happens. It would be like me saying to you, right, I've got a snooker ball here, and here's my cue, and I'm going to hit the ball with the cue, and then I do it, and you see the cue hit the ball, and at the exact moment that the cue hits the ball, all the lights go off, and then a minute later all the lights come back on again and all the balls are in a different position, and we missed out the bit where we watched them move and watched how they got into the new position. And you might think that that's irrelevant, and in fact there are quite a lot of physicists who would agree with you. I think I told you that Richard Feynman is famous for his catchphrase, "Shut up and calculate," which basically meant all he cares about is the answer. He doesn't really care about the in-between bit. He just wants to know what happens at the end. So you've got an equation, it tells you the answer, just shut up and do the calculation and just don't sweat the bit in the middle. But it's the bit in the middle that has caused the most headaches and is the reason why, after 100 years of developing quantum mechanics, it is still poorly understood, and it is still the cause of great angst with physics students as they try to learn it. So, to give you an idea of the craziness of quantum mechanics, you have to return to the double slit. The double slit is always referred to as the heart of quantum mechanics. If you can appreciate the serious weirdness involved in the quantum mechanical double slit experiment, then you start to see the true difference between the quantum world and the macroscopic world, and the true weirdness that is at the heart of quantum mechanics. And it is generally said that if you don't think quantum mechanics is fundamentally weird, then you haven't understood it. So I'm going to ask you now to watch a 9-minute video, which I won't stream for you. You can stream it yourself, and then we'll discuss at the end of the 9-minute video what it means. So I'm just going to post to the chat the link. Okay, it's 9:50. Can you click that link? And at 10 a.m. I'll start talking again. The idea here is that it's not okay to model those atoms passing through the slits in terms of just an atom and two slits. The atom has a wave-like nature which is spreading out into the universe around it. And it isn't only interacting with the slits or the atoms around the slits. It's interacting with quite a large volume of its immediate surroundings inside the camera. And it interacts differently whether there's a current flowing in the camera or not. The atom is somehow engaging with the world around itself in a deeply problematic way for physicists who like to draw an edge around what they call their system and have a closed system, that everything in the system affects what goes on inside the system and everything outside the system is irrelevant. Well, turns out that's not true of quantum mechanics. There's no edge to the system because wave-like particles have their little tendril-like waves spreading out quite a long way around where they're taking place. This has deeply divided physics, but it's not the end of the story. See, the wave equation that describes is not capable of telling you where any particular atom is going to land. The wave theory, unlike all theories before it, the quantum theory, is probabilistic in outcome. It will tell you that there is a 40% chance of particle that passes through the slit, so I think 17% chance of it arriving there, and a 0.00004% chance of it arriving there. And when you plot the probabilities, it looks a hell of a lot like the actual system, in the same way that, you know, you pour sand through one of those peg-like machines and all the grains of sand randomly bounce all over and it all ends up in a particular distribution at the bottom. You might have done that in maths when you were talking about Poisson distributions if you do A-level maths. The probabilistic nature of quantum mechanics is a consequence of the wave spreading out into its environment and somehow the theory trying to capture the idea that maybe it interacts with that bit there, or maybe it interacts with that bit there, or maybe it interacts with that bit there. Feynman constructed some equations, and the equations were so difficult to solve that he ended up taking a diagrammatical approach, a brilliant, inspired diagrammatical approach that he had borrowed from another place in physics and then manipulated to his own ends. Feynman's often referred to as the last polymath, the last great genius who knew a lot about a lot of different things. And so he was aware of something going on over here, and he thought, you know what, that's quite useful, I'll bring it and use it over here. These Feynman diagrams refer to all of the different ways that a particle can get from A to B by passing through every single eventuality, every possible thing that could happen between A and B. And you assign each one a probability and then you calculate all answers. Feynman's equations for anything than an electron orbiting a proton in a hydrogen atom. The equations are just hard. But that doesn't stop the philosophy from being debated, which is basically that physics has given up asking what happens between A and B. And even B, we've given up knowing exactly what happens at B, just the probability of various outcomes happening at B. Quantum mechanics has become, at its fundamental level, deliberately incomplete and deliberately probabilistic. And for people like Einstein, that just doesn't sit right with what physics is. However, we're 100 years on, and there is no doubt we've got really good at doing experiments. If you want to Google someone, there's a guy called Alan Aspect, who's a French researcher that has spent his whole career probing the truly weirdness of quantum mechanics. And he has done a lifetime's worth of inspired experiments about the weird aspects of quantum mechanics. And if his experiments are correct, there is no doubt that this is true. That fundamentally, subatomic particles are probabilistic in nature, wave-like in nature, that it makes no sense to ask what happens between a try to look, you will mess it up because you become part of the system. And that we can never be certain of anything anymore at the quantum level. We can only assign probabilities to the likelihood of different outcomes. Now, you either embrace that or you loathe that. Honestly, it divides physicists into camps just like Marmite does. And it has fractured physics for a long, long time. There were even different camps. You've probably heard of some of them. There's Bohr in Copenhagen, or was, he's dead. But the whole Copenhagen interpretation of quantum mechanics is one way of saying what the equations mean. You might have heard of the many worlds interpretation, which is a completely different way of interpreting what the equations of quantum mechanics mean. But fundamentally, nobody has yet been able to find an experimental way to determine any difference between the philosophies of what the equations mean. And so we come back to Feynman, who says, what do you care? You can't ever know what happens between A and B, so just let it go and enjoy your life and just shut up and calculate. I'll just finish with Schrodinger, because I'm sure you've heard of him and his cat. Schrodinger was in Einstein's camp. Despite the fact that he had helped to build the wave equations of quantum mechanics, he hated them, like Einstein, hated the probabilistic interpretation. So he said, well, this is just stupid, this whole thing about unplugging the camera or plugging it in. And he tried to come up with an example of just how stupid this was. So he said, well, tell you what, really depends where you draw the line, does it? Because what if we don't look at the screen? What if we leave the camera running, but we don't look? Does the universe know we haven't looked? Isn't that a bit like turning the camera off if we just don't look? So he said, you know, as long as I don't look, then surely the universe is still stuck in this probabilistic superposition state where anything could happen. There's still these probabilities of a particle landing here or here or here or here on the screen. Until we actually look where it did land, don't the probabilities still rule? Isn't that what quantum mechanics is saying to us? That the electron has a 40% probability of landing here, and until you actually look to check where it did land, those probabilities are real. That's what Feynman's saying. You don't know until you look, until you check what happened. So Schrodinger said, well, what if it's not particles through a slit? What if I have some really weird, evil contraption in which I take my pet cat and I put it in a box and I set up some contraption, some quantum mechanical contraption inside the box, and And I make it so that there's a 50% chance of a particle doing this thing here, and if it happens, it breaks a vial of cyanide and kills my cat. But there's a 50% chance of the particle not doing that thing, and the cat lives. And Schrodinger therefore constructed a system in which his cat had a 50% chance of being alive and a 50% chance of being dead. But unlike flipping a coin, the rules of quantum mechanics state quite clearly that until you take the measurement, until you look and find out what actually happened, then you're still in between A and B. And anything could have happened. And Schrodinger is saying, how can this possibly be that my poor little cat can exist in a dead alive superposition 50-50 indeterminate state? Schrodinger says that's just stupid. And he put out his idea of his to put forward this idea that cats cannot be alive and dead at the same time. Something must have occurred, whether there's a detector detecting the outcome or not. But actually, these days we would say, actually, that's fine. The cat can be alive and dead at the same time. Or maybe the cat knows if it's alive or dead. It's just that we don't. You can tie yourself in knots going round and round it. And for 70 years, physicists did. And that's why there is a lot of support for Feynman, who fundamentally just instructs us again and again and again and again. Just stop worrying about the weirdness of the quantum realm. We don't live there. We're not quantum beings. We live at a human-sized scale. Whatever is happening at the quantum scale is in principle unknowable. So don't worry about it. Just shut up and calculate. If you're interested, there's plenty of Googling to be done. But what I should, I guess, finish with is to be absolutely clear that nothing I have said today is examinable apart from de Broglie's relationship that the wavelength of a subatomic particle is proportional to 1 over its wave of its momentum. And we're going to spend tomorrow's lesson spending time investigating that idea. So today's just been a kind of introduction to the true heart of quantum mechanics. And if you want to go read about it, well, you got the rest of the day. I'm going to finish there, though. If you want to ask any questions, hang around. Otherwise, I'll see you tomorrow afternoon.
Thank you, sir.
Cheers.
See you.